Hello, and welcome to Chapter 8, Potential Energy and Conservation of Energy. This is for Aquinas Physics with Calculus. Today we're going over the OpenStax textbook, the OpenStax produced slideshow, and bouncing back and forth between the two, as shown here. I'll go over selected questions from the text. As always, this is not meant to be your sole source of information on this subject. This is simply meant to be one of many places you can get understanding. Feel free to peruse the textbook more, find alternative sources of this information, talk to your friends, your classmates, what have you. If you're getting stuck, always shoot me an email or comment, of course. I don't mind those one bit. And we can get going. Last thing I always say before this, of course, I'm expecting you to have at least a rudimentary understanding of physics at this point. So I'm not going to go over the details of how this integrated or how to run the equation necessarily. That's something I assume you're at this point. Potential energy and conservation of energy. What do we mean by that? Well, here we have an example of a Rube Goldberg machine or just a general marble maze, ball maze, where an object will travel essentially unaided by any internal motor, any internal producer of velocity. You have gravity working the entire thing there. And how can a very complicated looking maze like this be easily traversed multiple times by something as simple as like a pool ball, a billiard ball? Well, that relates back to the ideas of potential energy and conservation of energy. We've talked a bit about this already, but potential energy tends to refer to, among other things, the amount of energy something has to be released, and kinetic energy, conversely, is the amount of energy it has when it's released and what it uses to move. So here we have an example where at the start here, the football kicker kicks the ball. At this point, the ball has, when the ball is initially kicked, as in the ball starts to move, the ball has no potential energy in it because all the energy that was potentially in the foot has been put in the ball, and the ball is moving. The moving ball, therefore, has kinetic energy. As the ball increases in altitude, it is spending that kinetic energy to acquire potential energy, in essence. And when the ball reaches its highest point of its arc, its apex, if you will, then you have a potential energy maxima, meaning as the ball quite moved upward against the force of gravity, that's all stuff that's all place the ball has to fall back down. So a potential energy, according to gravity at least, is maximalized when you're at the highest point of your travel. And then as the ball, of course, continues to fall down, it is losing its potential energy, and it is again acquiring kinetic energy as it speeds up from the fall. So when the receiver catches the ball, it catches it at a point of maximum kinetic and minimum potential. Potential energy we'll get into here a bit later. It depends on what you're talking about. A spring has potential energy that's different from gravity in the way you describe what's happening, but the general concept of use of energy and storage of energy remains the same. If you're using energy, then that energy had to come from somewhere. A battery has chemical energy in it, and when you use that battery in, say, a child's toy, that battery energy is being converted into something else. At this level, we tend to think of using energy as moving and therefore kinetic, and we tend to think of potential energy as the energy used to create movement. In the real world, of course, there's huge varieties of types of energy, sound, heat, vibration, what have you. But that's just more complicated versions of this mathematics. We're at the start of the chapter, we're at the start of the book, at the start of the class of physics, right? So we're not going to go super in depth in those conversations. Big takeaway before we go into a mathematical example, of course, is you can think of potential energy as what you're going to do and kinetic energy as the doing of it. So let's take a look, example 8.2, and go over some of the math behind this. Here we have in the book, again, I think the book does a pretty good job of simply laying out these concepts, including but not limited to the equations. Here, 8.1 is an equation relating potential energy involved and relating it to things such as work, the capital W, which is something we already talked about. A key component that we'll get to here in a bit is, in general, you cannot not use energy, and you cannot store energy in a way that it cannot be used. The fancy way of this phrasing is conservation of energy. Any energy you put in comes back out. The football at its apex, is going to have so much potential energy, and when the ball is caught, the speed of which the ball is caught is directly related to how high up it was. The more something falls, the faster it falls, right? That's conservation of energy. If I dropped a ball from 5 feet and a ball from 10 feet, and the ball from 10 feet was not going proportionally faster than the ball from 5 feet, I'm breaking the laws of physics. Please don't do that. Please don't break the laws of physics. That would not be a good thing. In reality, of course, we have explanations for where the energy goes against heat, sound, light, things along those lines. And when we get to, I think, part 3 of this, conservation of energy, and I guess even part 2, non-conservative forces, we're going to kind of show if the math doesn't add up, then there's something else to it. But again, for simple sake of conversation, to not go super in depth in the things we don't need to go super in depth into, the amount of energy you put into something is the amount of energy you get out of it. You don't get out more, you don't get out less. All right. With that all being said, let's go over question 8.2 here. So you are hiking the Great Blue Hill in Milton, Massachusetts. That's about 147 meters above its base and has elevation above sea level of 195 meters, as shown in the image here. Stuff about the Native American name of it. A 75-kilogram hiker ascends from the base to the summit. What is the gravitational potential energy of the hiker Earth system with respect to zero gravitational potential energy at the base height, where the hiker is A at the base, B at the summit, or C at sea level afterwards? So we talked about this in previous chapters, but the most basic form of potential energy is how high you are above something, because that dictates how fast you're going to fall. Jumping off the roof of your car versus jumping off the top of a building would be very different on your knees, right? And the math behind it is what we're going to go over here. So how do we solve these problems? How do we solve the gravitational potential energy of the hiker at A, the base, B, the summit, and C at sea level? Well, first, we need to pick an origin of the y-axis and then determine the value of the constant that makes potential energy 0 at the height of the base. Then we can determine the potential energy from equation 8.5, this one right here, which, again, I keep saying again, it's kind of what I do. When you go through these questions, you always want to find the appropriate equation that best covers all of your knowns and unknowns. In this example, we have an equation for the potential energy of a system, big U sub y, which is equal to mgy plus a constant. M is mass, g is gravity, y is along the y-axis, plus some constant, which you would care about based on the question. So given that equation, mgy, we can then set our y-axis up to be able to solve the question as stated here. So a 75-kilogram hiker ascends from the base to the summit. So starts at the base, goes to the summit. Given that sentence, what is the gravitational potential energy at the base of the hill? Well, we are setting this question up so that the base of the hill is where we're starting. So that's our y naught, right? So if our y naught is zeroed out, therefore y equals 0. MGH would therefore be 0. So the sea level the base of the hill's potential energy is 0 because that's where we're starting. When we climb the hill, some 147 meters, we then multiply that into our equation for our y, or our height in this case. Y is 147, our mass, 75, and gravity, 9.8. Multiply those simply out, and we get 108 kilojoules of energy. The top of this hill, you have 108 kilojoules of energy. If you were to fall into a black hole at the hill and just careen on down, you'd spend 108 kilojoules of energy before you hit level to the base. Now, why I chose this question is it also asks at sea level. Sea level is below the base, but we set the base to be equal to 0. So while you can go, while the base of the hill is higher than sea level, we have decided the base of the hill is 0. So whatever's below the hill would be a negative number, therefore. So sea level has negative 35.3 kilojoules of energy at that point. You have dropped some 75, well, not some 75, some 48 meters below your 0 point, landing you, as we said here, at a negative potential energy. Practically, what does that mean? Well, it means we decided that 0 was the base of the mount of the hill. That's practically what it means. Potential energy always goes to the source of the gravitation, since gravitational potential energy always goes to the source of the gravitation. But in practice, we don't care about that because the source of the gravitation of the Earth is the infinitesimally small point at the center of the Earth. But practically, why would I care about that when I'm doing my math? I'm never going to get down there, right? Should I care about the sun's point of gravitation? Should I care about the great attractor, the center of the Milky Way galaxy? No, of course not. Those are necessary to any question I'm actually going to ask. So we set up all of these energy conversations to be something that we can actually solve and care about. And again, potential energy is very, the equations, I believe, are rather straightforward. Here we have elastic potential energy. This essentially is a spring. It's the most common way we think about it. And it is based on 1/2 kx squared, k being a constant of the spring, of a plastic spring versus metal spring, x being how much you're moving it, and 1/2 is part of that component plus any given constants that we care about. So it's the exact same conversation, just to use a different equation. Here's examples in the text about that. I'm not going to go over them because it's kind of the same basic conversation there, right? And that's what's going on here. So instead of height above or below a certain point, it's movement of the elastic thing you're talking about. Classically, we just say a spring because they're very easy to understand. You take a spring, you pull it down some number of meters and release it. The further you pull it, it's going to indicate how much it bounces back and forth, right? When bungee jumping, of course, is something you care about. You want the bungee cord to be long enough to give you a good free fall, but short enough to where you're not going to smack your head on the ground as the cable extends. And those things are calculated out in a very similar manner to exactly the equations we've been talking about here. So that is the basics of potential energy. Now let's move on to the idea of using that potential energy. So when you use a potential energy in some way, it doesn't matter what it is, you output always the same amount of energy. But the output of that energy varies depending on the real world situation you're dealing with here. To simplify things at this level, we discuss it in terms of conservative and non-conservative forces. Conservative forces are kind of the point of using the energy, and the non-conservative forces are all the other stuff in reality that zaps energy away. You've probably heard of perpetual motion machines, how they're impossible. That's basically because of non-conservative forces. You can't do something and not have drag or friction or something like that affect it in some way. You can greatly reduce friction, for example, right? Ball bearings, stuff like that. But you can't negate it enough to where 100% of your input comes out. we have not figured out a way to do that in any meaningful sense. So I'm sorry, perpetual motion doesn't exist. I apologize. I know it's breaking your heart here. So let's go over an example 8.5 to understand this process. Oh, and also before I get to the example, it's important to understand the math, of course. Here we have various integrals relating the work done in a system and the forces involved. And the key takeaway from all of these equations is if you conserved all your forces, then what you got in is equal to what you put out, or the amount of work done is equal to the amount of work that could have been done. If you run into a situation where you do not get the same number out, then you have some non-conservative force acting on the situation. Again, friction, air resistance, drag, you name it, sound, light, whatever. These equations are basically what are you doing, and then let's integrate it out to find out the result. This here 8.10 is the differential version that I'm talking about here. So the differential of f of x with respect to y is equal to differential of f of y with respect to x. The work energy theorem basically saying if you get out what you put in, then you've used all your forces correctly. That's kind of only in paper math that you get out what you put in. Usually you lose something, but if you account for what you lose, then you're doing a better job of understanding the system. So here we have the grind wheel as an example. A grinding wheel applies a non-conservative force because the work done depends on how many rotations the wheel makes, making it path dependent. Then if anyone's ever used a grinding wheel before, you know they jump everywhere, right? And a proper use of a grinding wheel is going to be smooth, simple motions, grinding down the path you need to, that grind another thing in the path that needs to be ground. The more you jump around, the more you waste, the more time you waste not grinding the thing. What happens when you grind something down? Sparks fly up, makes a lot of noise, right? Those are all the non-conservative forces taking the energy away from the grind. The smell, even, is a byproduct of the release of the energy that's not going towards the grinding process itself, because that's nature. That's how nature works. So let's go over example 8.5 to go a bit more into this concept using no numbers. So I give you 3 example equations here. And I can ask you which of the following two-dimensional forces are conservative and which are not. Again, a conservative force, by definition, is you get out what you put in, or what you're doing results in the same thing. So we can look at this one here, ax y cubed I hat plus ay x cubed j hat. And if we differentiate those two according to x, f of x sub y and f of y sub x, we get, in fact, different equations out. So as you're moving the force, for example, in the x direction, you get a different result here, 3ax squared, than when you move it in the y direction, which would be 3ay squared. Why? Well, because they're different equations, right? So you have a non-conservative force because your results are different depending on what you're doing. And I can take that exact same example here, and I can, again, go over part B, where it's a multiplied by the quantity of y squared over xi hat plus 2y natural log of x over b j hat. And then when I differentiate these things according to x and y, I end up getting, when I differentiate these things according to x and y, I end up getting, in fact, similar results. I get the same thing, which is, if I'm going, the force along the x-axis results in a 2ayx, and the force along the y-axis also results in a 2ayx. How does this happen? Well, because according to the way I'm putting this information in, I'm getting out the same result irrespective of the force I put into it. Meaning I have a conservative force, or things differentiate down to that single same variable. If I can do this again for my third option, I keep ending up at, and if I end up at the same answer, irrespective of what I differentiate by, that I have a conservative force. Again, a conservative force means that you're getting out what you put in, which is not reality, but part of the mathematics of it. And then you, of course, can take all the additional stuff into account when you learn it. This basic concept of a conservative and non-conservative force in a mathematical sense can, of course, be expanded out as big as you want it to be, right? You can go third, fourth, fifth dimensions. Yeah, it's do your do your differentials right, essentially. So I hope that concept lands decently well. You need to It's important to take away not only the physical property of what a conservative or non-conservative force is, but also the mathematical approach, namely as shown here in equation 8.10. Make sure that your answers are equal to what's being asked. If that's what a conservative force is, the energy you put out to do the work is equal to the energy put into it. We can have these sort of conversations with pendulums that happen quite often. The book has two good examples of going through that process. And then when you actually differentiate the movement of, say, a pendulum back and forth, you can graph out the potential and kinetic energies relating to that movement to find out that, again, if we're not taking into account the non-conservative forces, we have this idealized perfect world, your total energy output is always going to be the same, because at the start of the pendulum, you have maximum potential. At the fastest point of the pendulum movement, at the lowest point, down here, you have maximum kinetic, and then back up here, you have maximum potential. And throughout this entire conversation, your total energy doesn't change. Again, go through the text as examples if you want to see the math behind it. But it's kind of a cool little concept, right? If these were moving images, the orange ball would never move, and the purple and the green would bounce up and down perfectly in sync with each other. The more you do, it's the same song and dance each time. This example here, the helicopter is something falling, which we're skipping as well, because I want to go over example 8.9, which I think is more interesting. Well, again, you can look at the examples here, potential and kinetic. K is kinetic, U is potential. I don't know why they chose U. I never quite got that. Whatever. To solve out these problems. So here is 8.9, a constant acceleration problem using equation 8.14. I chose this one because that equation looks gross, right? So what are we dealing with here? Use the potential energy shown here for energy equal to greater than 0 in equation 8.14 to find the position x of a particle as a function of time. So what is equation 8.14? Equation 8.14 is shown here, and it relates the kinetic energy of something to its velocity changing with respect to distance, right? So we can illustrate some of the simple features of the energy-based approach by considering a path of one-dimensional motion with potential energy u sub x right here, and no non-conservative interactions are present. So if we say no non-conservative interactions are present, then we're doing perfect world, no friction, just care about the numbers here. So we take our kinetic energy equation, 1/2 mv squared, and we realize that that is in fact the energy minus some potential shown here. And then when we solve out v, well, velocity is dx over dt, right? So if we substitute in the dx over dt for what we're doing here, and we solve that for v, we get an equation relating velocity to the energies given from the initial 1/2 mv squared conversation, and potential energy being removed from the total energy, E, of course, being total energy. So if we take that whole conversation there, we separate the variables x and t and integrate along time t, given a distance change, x naught to x, we land on a very big looking equation relating our change in position to our time based on our total energy and our potential energy being used. So when we go and we calculate potential energy given this negative change in energy with respect to position, it sounds a lot, but since we know how potential energy changes as a function of x, we can substitute that ux that we're given into equation 8.14, shown here, and integrate and solve over for x. When we do that, the result is an expression of x as a function of time that relates to energy, the mass, and the initial position. What does all that mean? Well, if I take my initial equation here, the dx over square root of 2 times the quantity, energy minus potential, all that over m, which is mass. Notice I'm taking my equation, negative e x over x naught, and I'm plugging that in for u sub x, right? When I plug that in for u sub x, I'm left with two e's because I have an e here, and then my x naught thrown down the bottom, and my x is already standing from my initial x. So simplifying stuff down, caring about that dx and integrating on through, lands me, funny enough, at an equation that solves for x naught based on some component, solves for x based on some component t given a t shown here. So the reason I wanted to go over this is to, again, remind you that following your simple calculus understanding, going back and thinking about how to integrate something, what do you do with division, worrying about all that jazz, and throwing in x's and x naughts, these questions are not difficult if you understand the calculus behind them. You can run into issues if you're like, well, crap, I forgot some of my Calc 2 or something like that. But these are essentially word problems, right? These are examples using quote unquote real world letters, but you're still following the math the same. So I hope looking at this, you can follow what's being said there. If not, you need to tell someone and we need to catch you back up. And so I wanted to talk about that. Last conversation really is over the diagrams and the stability. This is essentially graphing potential kinetic energy as it moves back and forth. Again, if you understand the basic concept of you use your potential as you move. When you stop moving, you stop building your potential again. These graphs all kind of look the same. Here we have, there we go. Here we have a graph related to a question from 8.10, which I'll go over now. I keep saying this. I'm skipping through a lot of these pages. If you're going through and you're not understanding what's going on with the questions, read through this stuff more slowly. It'll land pretty decently. That's a very important skill to have. So, example 8.10. The potential energy of a particle undergoing one-dimensional motion along the x-axis is shown here. The potential is in joules, and x is in meters, of course, that's our units. The particle is not subject to any non-conservative forces, so perfect world. And its mechanical energy is a constant negative 0.25 joules. So, given all the information, is the motion of the particle confined to any region of the x-axis, and if so, where? And are there any equilibrium points, and if so, where? And are they stable, unstable? Are they going to stay in that way? So let's take this equation, let's graph it out. The 2 times x to the 4th minus x squared results in this W shape. Cool. The function is a 0 at the origin, right here. Good. And again, the y-axis is potential energy in joules. The x-axis is position in meters. The function is 0 at the origin, becomes negative x increases in the positive or negative directions, because, right, x squared is larger than x to the 4th when x is less than 1, and then becomes positive when x is sufficiently large, when you have a sufficiently large absolute value of x. Your graph, again, looks like a double potential well, a W, with the zeros determined by the equation when x is 0, right? Your potential is 0. And the extremes are determined by the first and second derivatives as shown way out here, right? Cool. You can find the values of A, the allowed regions along the x-axis for the given value of the mechanical energy from the condition that the kinetic energy can't be negative. What does that mean? Well, kinetic energy is mv squared, right? You can't have a negative velocity because it's squared. You can't have a negative mass by definition. So that gives you your allowed values of mechanical energy. And given the equilibrium, and you can also find, as again said, equilibrium points and the stability from the properties of the force relating the minimum maximums of the potential energy. So to find set allowed regions for X, we use the condition of the energy minus the mechanical, the total energy, minus the potential gives you your kinetic. And that, of course, would be equal to a quarter, which is your total energy, given up here at the top, minus your equation, which is greater than 0 because you can't have negative kinetic energy. And if we complete the square of x squared, the condition simplifies very easily to what is shown here. Solving this guy out, 2x squared minus 1/2 squared is less than or equal to a quarter, lands you at a property shown in the center. This represents the two allowed regions where you have, as set up here, a motion confined to the x-axis. So is that right here and right here, right? From 3.8 to 9.2, oh, that's what it was. This guy's the R and the P and the R. So there we go. The P and the R show you where you get that positive, real kinetic energy. And then those equilibrium points are solved by differentiating out u with respect to x, and then finding, again, those locations where x equals 0, and then x is positive or negative of that center point, and that center low point, forgetting the technical term for that, not minimum, not local minimum, maybe? I can't remember. That point that we're discussing here. So given some xq of 1 divided by square root of 2, or about 0.707 roughly, we land on an equation giving you those points. Why do we care about this jazz? Well, the particle in this example can oscillate in the allowed region from either of the two stable equilibrium points we found, but does not have enough energy to escape from the potential well it happens to be initially in. So this stuff way out here isn't what the particle is actually restricted to being in. Interesting, right? The conservation of mechanical energy and the relations between kinetic and speed and potential and force enable you to deduce quite a bit of information about the actual motion of some particle following, again, the equation that we showed up here. There's some interesting information, interesting takeaways from this jazz when you go about and you do the math, and that's why the calculus side of this stuff is super cool. The last bits here involve energy in the real world. Essentially, as shown here, all the different ways. Energy in the most common way we use is electricity or food, right? Those are like the two forms of energy that we actually care about. Electricity can come from a huge variety of sources. The vast majority of the world's energy, of course, is fossil fuels, oil, natural gas, the big two, and coal is another big one as well, of course. There's a big push towards renewable energies. Who knows how it's going? You know, ask your local politician this week and put on renewable resources, and you'll get very different answers. I hope to live in this bright, beautiful future of sunshine, lollipops, and solar energy all throughout. I don't know if it's going to happen, but it would be kind of cool. So again, if you want to go more in depth into 8.5, go ahead and read it. There's some good information here. this lecture is more so focused on the math. So that is chapter 8. As you could see, especially in that last example, we all kind of diving deep into using calculus to solve problems. That's part of the game plan here. I wish you all the best in your endeavors. Just take your time, right? Real picture again what you're doing, picture how it works, what the other things mean, and try your best to follow the steps in a slow, continuous pattern. When if I'm giving you assignments, I'm looking to you to show your work. I'm looking to follow exactly what you have written down. If I can't follow what you're doing, but you put the right answer, I gotta wonder where you got it from. So I care more about the process than the end solution. Being said, thanks for watching and take care.